Good afternoon, everyone. So my name is Zhang. I'm a graduate student at Rutgers University. So I'm very glad to be here today to present work, evaluation of existing pre-stressed concrete bridges and live load distribution. So this is a collective work of also two of my colleagues, Dr. Pang Lu, who is a research associate at Rutgers Infrastructure and Monitoring and Evaluation Group, and also Professor Hani Nassif, who is the professor and the director of the group. So let me go to my presentation. So just a little bit background. In the state of New Jersey, there are about 1,500 pre-stressed concrete bridges, and there are about 43% that were built between 1950 and 1980. So the historical existing bridges may have seen some trucks that's heavier than their original design load. Also, they may have been inadequately designed from the current design point of view. So here, I put two code here on the figure. On the left-hand side, this is the earliest design code published by Bureau of Public Road, the criteria for pre-stressed concrete bridges in 1954. And currently, we're using the AASHTO-LRFD bridge design. Put the edition of 2017. So there has been 60 years of evolvement of the code, and from the earliest one to the current one, the earliest one is only about 30 pages with limited guidance. Up to now, we have this LRFD, which is more comprehensive. So the study is aimed to evaluate the safety of the historical existing pre-stressed concrete bridges from the following three aspects: the design capacity reserve, live load distribution, and live load carrying capacity in terms of the current design load. So here's a part of the summary for the shear provision. As you may see here, the shear provision has largely changed and differently from the earliest design to the LRFD design. So the review of the historical design have indicated that the prediction of the shear resistance was inconsistent between the era. So the first code is based on the shear design of the first code is based in 1954 was based on the limiting the nominal shear stresses. So there are two load combination. One is the working load, one is the ultimate load. The coefficient for the two load combination is different, but they're based on the concrete strength times the effective area of the shear concrete. And also it's noted that the web reinforcement resistant estimation is based on the, was found by the researchers that the shear resistance is calculated based on the truss model, which is the same as reinforcement concrete for the earliest design code. And also there's maximum spacing limitation for the design code. But one of the things that we found is that some of the old provision may have overestimated the contribution of the concrete. So for example, here, for the ultimate load, they use the 0.08 FC prime for the concrete strength. As an example, if a typical concrete of 34.5 megapascal will result in 2.76 megapascal for the concrete strength contribution. However, when they changed to, when they adopted in the AASHTO Standard Specification, they reduced that contribution to 0.3 in the 8th edition and 0.6 in the 9th edition. So the concrete contribution could be overestimated in the earliest design code. And also there are some specification says the design at the shear should be choosing at a quarter span, which we now know the support is the most critical location. And also we did the review of the distribution factors and also the live load and also the flexural design. So for the flexural design, the design theory has always been limiting the stresses within the permissible limit. So the service load will control the design, also in turn control the flexural design of the pre-stressed girder. So theoretically, historically speaking, the stress has always been consistent. Stress design has always been consistent and reliable. And for the distribution factors, the live load has been changed from the earliest design to of HS20 to the current HR93. So there's a need to evaluate also the load combination of the design load. So there's a need to evaluate the behavior of the structure and to overall evaluate the behavior of the structure. So in here, the consistency and the capacity reserve of the existing bridge are evaluated here, and we picked the actual bridge for this study. All of them are designed based on the earliest design, which is stated in their as-built design drawing. So the bridge were first redesigned with the minimum requirement shown here, and also they were compared with the as-built bridges, the low rating factor of the as-built bridge shown here. So the objective here is to first, there are two objectives. First is to do the low rating based on the LFR of the design load to evaluate the safety and from the current point of view, and also the comparison between the minimum design, the minimum redesign and the as-built design will indicate how much capacity reserve were considered during the original design phase. So the first thing here is the baseline where the as-built low rating shows that the average mean value of the inventory moment low rating is about 1.75, and for the shear is about 1.32. You can see the also the standard deviation of the shear design is higher than the flexural, and so if we were looking at the redesign of the shear bridge of the shear low rating, you can see while there are 13 out of 17 bridges show that the redesign, although satisfy the minimum requirement, but they were unable to pass the inventory design level from the current design point of view. However, for the shear, for the moment, they all passed except for one, which is slightly less than 1.0, with a mean of 1.26 and the standard deviation of 0.16. For the shear, there's much higher variation. So if we compare the redesign and the as-built design, and we will know that how much capacity reserve were considered. So for the moment, you see there's a consistent, conservative capacity reserve about on average 29% with a standard deviation of 0.12, and for shear it's about 42% with a very high standard deviation, and with some of the bridge may be under designed in this case. So we did one of the bridge to do the field testing of one of the pre-stressed concrete bridges. We used the Smith hammer to estimate the concrete strength, the institute concrete strength. We also used the GPR to verify the as-built drawing for the shear reinforcement. We found from the Smith hammer, we found the concrete strength, and we used that to update our front element model. I'll show later. So we also did a diagnostic load test, dynamic load test on 4 of the passes on that bridge. We did 3 runs for each pass, and the consistency was checked. So the strain was installed on the bottom and also top of the girder to get the structural responses. And we used that information to verify our ABAX model. So the measured strain was the measured strain and the simulated strain are showing here, and I'm showing 2 of the typical plots. So we are picking only the girder that's directly under the vehicle load. For example, for path 4, we're picking the girder 1 and girder 2. And so also we use the top strain to validate our model, and we found the composite action was and based on the neutral axis analysis, we also found the composite action exists for all of the girders. And so based on that, we verified model and used the verified model to virtually do a distribution test. Since the traffic location might not be the most governing case for the distribution factor, so we moved the truck every 2 feet to obtain the maximum distribution factors, and we compared that with the LRFD. So the distribution factors are calculated based on the there's two equations for both shear and flexure, and we calculated based on LRFD, and we found that the percentage differences is about 20 for the most critical location for the flexure design, for the flexure GDF, and for the shear is about 10.5%. And later on, we did a similar FEM modeling in the AASHTO BRR to compare with the other four available approach to estimate the distribution factors for both shear and moment, and for G1 is the single lane moment, a single lane distribution factor. GM is the multiple lane distribution factors. So all of the approach, so here in this table, the negative sign shows the design is unconservative, and the positive sign shows the design is conservative. So we also calculate the sum of square to evaluate the performance of the each methodology, which the baseline here is the FEM analysis. So the red one indicate the best performance for each distribution factors. So we found that for the standard specification also is the distribution factor from the earliest design. It has there are 13 cases out of 17 cases underestimate the distribution factors by for the multi-lane, they underestimate the distribution factors by average of 11% for multi-lane. And so here is the summary and the conclusion. So based on the earliest design code, we get a database of bridges that was built based on that. And from the historical review, we found the stress design of the pre-stressed concrete is consistent, and the minimum design satisfied the current LRFD inventory design level. So all bridges had positive capacity reserve. And for the shear provision, the shear provision may have produced inadequate capacity to pass current design load rating. So there are 5 out of 17 bridges were found being under design with negative capacity reserve. So this design error should be highlighted with potential load shear rating, low shear rating, and using the validated finite element model, we calculated the distribution factors, and the results show that the governing distribution factors estimated by the RFD are conservative. And the last point is the distribution factor are analytically calculated using the FEM method and compare with the other 4 approaches. So the available approaches are mostly conservative, while the AASHTO standard specification underestimate the shear distribution factor. So yeah, I would just like to acknowledge the sponsor for this study, the New Jersey Department of Transportation, and also financial support from the Tier 1 University of Transportation, C2 Smart at New York University. And thank you for your the listening, and I would like to answer any question if you have.
All right, thank you for your presentation. I did have one question for you. In terms of this study, it seems like you conducted some of the study and the field test, perhaps because the inventory or operating ratings were poor. Was your work implemented back to the bridge owners, meaning, changing of the rating factors, or is that still to come? Or
I think it's still to come. I'm not sure if this has been updated to the inspection report. Yes, yeah, this study is sponsored by the New Jersey Department of Transportation, and we did this to verify their rating factor as well.